This is the screencast for section 2.1, example 6. We're going to explore non-existent limits. So everything you've seen up to this point had a limit. The function may not have been defined at that exact value, but the y values were approaching a specific value to, in other words, the limit. So here, the directions kind of give it away. They say use a graph to show that the limit as x approaches 2 of this value does not exist. Okay, so you would tell me what you put into y1, you would tell me the window, and then you would draw a little sketch of the graph. But another thing we also learned in pre-calc is that it's really important to show graphically and algebraically that things line up to make sure that we're right. So let's look at this algebraically. We learned that in order to find the limit, all you have to do is plug in the value you're trying to find the limit at. Well, when I plugged in the value 2, I did not get 0 over 0, so there is no removable discontinuity on the function at x equals 2. So that's why, as you know from pre-calc, there's an infinite discontinuity here. There is a vertical asymptote at x equals 2. So from one direction, the function approaches positive infinity. From the other direction, from the left, it approaches negative infinity. So we don't have a specific y value that the function is getting closer and closer and closer to. So you might say something like, since f of 2, so when I plug in 2 to the function, I don't get 0 over 0, then that means the limit as x approaches 2 of f of x does not exist, because the graph does not have a removable discontinuity at x equals c, and our specific c value is 2. It has an infinite discontinuity. Let's look at number 29. We're going to just attempt to find the limit in this case. So I'm going to plug in 1 into the numerator and 1 into the denominator. And I get negative 3 over 0. So that means the limit as x approaches 1 of x squared minus 4 over x minus 1 does not exist because f of x has an infinite discontinuity at x equals 1. And we're going to show that graphically as well. And you can see from the graph that at x equals 1, the function has an infinite discontinuity where the left side approaches positive infinity, but the right side coming in from the right approaches negative infinity, so the limit does not exist.